Hello viewers, this is the video lecture to present on topic for the subject theory of computation, and the topic is conversion from Epsilon Nfa to Nfa from the second unit. And the objectives are to understand the concepts of Epsilon Nfa, to analyze the problems for converting Epsilon Nfa into Nfa. First of all, let us remember the concepts of non-deterministic finite automata. We have to understand the concepts by differentiating NFA, non-deterministic finite automata, from DFA. In DFA, in deterministic finite automata, from a state for a specific input symbol, only one state transition is possible. But in non-deterministic finite automata, from a state for a specific input, more than one state transition is possible. That is, from a current state, by applying the specific input symbol, it will produce more than one new states. And also, another one important feature of NFA is NFA can make the state transitions without consuming any symbol. That is called as epsilon move. And NFA can be defined with the help of 5 tuples in standard definition. Capital letter Q is the finite set of states. Sigma is the finite set of input symbol. Q0 is the starting state. Capital letter F is the final state. Delta is used to represent the state transition function. Then we can see NFA with epsilon move. Previously we told NFA can produce the null moves. That means in NFA, state transitions can be possible without consuming any valid input symbol. In such cases, that state transitions will be considered as the epsilon moves. So if any FA contains epsilon transactions or epsilon moves, such finite automata is called as NFA with epsilon move. And another one property associated with the NFA is epsilon closure. That is, epsilon closure for a given state A means a set of states which can be reached from the state A with only null move, including the state A itself. Now we are going to see the problem for the conversion of NFA epsilon to NFA. To obtain NFA from NFA epsilon, we have to eliminate the epsilon transitions. If epsilon transitions are eliminated, then some non-epsilon transitions should be added to substitute in order to maintain the language accepted by automata. Now we are going to see the definition of NFA corresponding to NFA with epsilon transitions. So we will use sigma dash for sigma, delta dash for delta. Q0 is the starting state. In both cases, both in NFA epsilon and NFA, the starting state will be same and the final state will be varied. When we convert the NFA epsilon NFA into NFA, the set of states will be same, that is capital letter Q, and the final states may be varied. For NFA, for the resultant NFA, the final states will be considered as F dash. Now we are going to see the problem. Construct an equivalent NFA without epsilon moves for a given automation. The automation is actually epsilon NFA system. The automation is represented with the help of diagram, state transition diagram. From the diagram we can see there are 3 states, Q0, Q1, Q2. Q0 is the starting state, Q2 is the final state. And in between the state transitions are performed by null moves, epsilon. So if we apply epsilon to one edge, we should understand the state transitions are performed without consuming any valid symbol. So here the valid symbols are 0, 1, 2, but system is changing from Q0 to Q1 without consuming any symbol. So in such case we should mention the symbol epsilon, that is null move. Similarly, the system is changing from Q1 to Q2 without consuming any symbol. In that place, we have to mention epsilon, that is null move. And from the diagram, we can construct the transition table. We have to list out the number of states and the number of symbols. So when we mention the number of symbols, we have to add the one more symbol epsilon, and we have to mention the corresponding state transitions in the table. Now we are going to derive functions to construct the correspondent NFA without epsilon transitions. First of all, we are going to define the epsilon closure for each and every states in our system. Our system consists of 3 states, Q0, Q1 and Q2. So we have to first of all derive the epsilon closure for Q0, Q1, Q2. The epsilon closure for a state is the set of states reachable from the state by accepting only null moves. And when we write the epsilon closure, we have to include the same states also. Same state also. So epsilon closure of Q0 is, we can see from the diagram, the states reachable from Q0 by applying only epsilon is Q1, Q2. But when we write in the definition, we have to include Q0. So epsilon closure of Q0 equal to Q0, Q1, Q2. Then epsilon closure of Q1 equal to Q1, Q2. And epsilon closure of Q2 is equal to simply Q2. Now, this is the main thing we want for our process. Next, we are going to follow one important rule for the conversion process, that is del dash of Q comma A. Del dash of Q comma A is the state transition function for the resultant NFA without epsilon transitions. So del dash of Q comma A equal to epsilon closure of del of epsilon closure of Q comma A, which is the rule. By applying the rule, we are going to do the derivations to identify, to produce all the delta functions for all the states, and for each state we will find out the delta function for all possible combination of input symbols. So first of all, we will identify for del of Q0, 0. In the right hand side, we have to apply the previous rule. So del of Q0, 0 equal to epsilon closure of del of epsilon closure of Q0, A. So in that place, inside the bracket, we have to substitute the value for epsilon closure of Q0. So that is Q1, it is the set of Q1, Q2, Q3. In the next step, we have to separate the delta function for the individual states. Del of Q1, A, union del of Q2, A, union del of Q3, A. Then after that, again we have to substitute the value of del of Q1, A, Q2, A, etc. from the table. We have to substitute the values of the del function from the table, transition table. And finally, we are concluding that epsilon closure of Q0, and again we have to substitute the value from the previous epsilon closure definition. Similarly, we have to derive the delta functions for all the states. For each state, we have to derive it for all the input symbols, like del of Q0, 0, Q0, 1, Q0, 2. Similarly, del of Q1, 0, Q1, 1, Q1, 2. Del of Q2, 0, Q2, 1, Q2, 2. So we have to expand the epsilon closure function. We have to separate the epsilon closure for the different states. We have to substitute the values. Finally, we have to substitute the values from the table. So in this way, we have to derive all these delta functions. Then, and another one important thing is, we have to identify the final state for the resultant NFA, and for that we will follow one rule, that is F dash equal to F union starting state. F dash is our final state for our resultant NFA. Here, if the epsilon closure of Q0 contains a member of F, we have to include that state to our final state. That is, F is actually in our from our given system, our final state is Q2. Okay, our final state is Q2. So Q2 is the member of epsilon closure of Q0, isn't it? So we should remember epsilon closure of Q0 equal to Q0, Q1, Q2. So F is in our system, F is Q2. So Q2 is the member of epsilon closure of Q2. Since it satisfies the condition, we have to add Q2 along with Q0 as our final states. So our final states will be Q2 union Q0, that is Q0 and Q2. Both state will be our final state. Now we are constructing the transition table and diagram for our resultant NFA. Simply we have to substitute all the delta function values in the table. That is, we have to check what is del of Q0, 0, what is del of Q1, 1, 2, what is del of Q2, 0, 1, 2 from the previous derivations. Substitute, place the values inside the table, and from the table we can draw the automation diagram for the resultant NFA. So already we have decided two states are final states, Q0 and Q2. Then from the from the table we have to apply the edges. Like for example, when we apply 0 to Q0, this new state is both Q0 and Q1. And when we apply 1 to Q0, the new states are Q1. So in this manner, by checking all the values, all the transitions from the table, we have to construct the diagram. For example, from Q0, when we apply 1 to Q0, the new states are one is Q1, another one is Q2. Or we can say when we apply 2 to Q0, the next state is Q2, simply Q2. So the same things will be constructed as the transition diagram. So this is our final transition diagram for the NFA, non-deterministic finite automata, for the given epsilon NFA. Okay, thank you all.